Guys, this recording is going to take care of the notes for lesson 4.1. And if you'd like to have a copy, I'll have a copy of the PDF file that will be the notes that you can download, that you could just go ahead and print out and follow along as you watch the video, or you can take notes yourself and as you watch the video. And that's probably what I would recommend, that you take notes just like you would if you were in class. Lesson 4.1 is titled Antiderivatives and Indefinite Integration. So, antiderivatives and indefinite integration. And we want to start with a pretty basic idea. We've done a lot of work with derivatives, and we know, theoretically at least, we know lots of different rules for finding derivatives. Now we need to kind of think about working backwards. For instance, if we have some function f of x, and f of x is defined as 3x squared, can you find a function that is the derivative? So what I'm asking you to think about is, can you find some function, capital F? My handwriting is especially challenging this morning. Alright, so the derivative of capital F is 3x squared. So I'm asking you to think, what function can I differentiate and have the derivative be equal to 3x squared? Why don't you pause the recording, give that some thought, and when you get it figured out, when you think you know what the function capital F of x would be, go ahead and start the recording again and see if you and I agree. Capital F of x equals x cubed is one function that we can differentiate, and the derivative be 3x squared. Now, something kind of interesting to think about is that's not necessarily the only function whose derivative is 3x squared. What about maybe x cubed plus 5? Think about that. If you differentiate, derivative of x cubed is 3x squared using the power rule. Derivative of 5 is 0. Okay, so there's evidence that x cubed plus 5 is a function you could differentiate and get 3x squared. Another possibility, maybe make that look better. Maybe, maybe I'll get it written down right. Maybe x cubed minus 12. Think about what the derivative of that function would be. 3x squared, derivative of 12 is 0. So 3x squared would be your derivative function. So basically, any function, x cubed plus 5, x cubed minus 12, any function that contains the term x cubed and then a constant term, added or subtracted, it doesn't matter, would be referred to as an antiderivative of f of x. So these things that I've circled in red are examples of antiderivatives. Of our function f of x that we were given to begin with, which was 3x squared. So a formal definition of an antiderivative. A function capital F is an antiderivative of lowercase f on some interval I if this statement is true. The derivative of capital F of x is equal to lowercase f of x for all x in the interval. Now, I do want you to notice the fact that I've used the word an antiderivative instead of saying that our function capital F of x is the antiderivative. And I did that on purpose. That's not just a grammatical error. That's actually true because there are actually an infinite number of functions you could differentiate to get 3x squared. We can kind of handle all the possibilities for this function f of x by doing this. Let's say lowercase f of x is 3x squared. The antiderivative of that function could be written as x cubed plus c. So we're showing that any constant c could be added to x cubed, and we still have a function whose derivative is going to be 3x squared. Now, at this point, it's a good idea for us to talk about some vocabulary. Just like when we started working with derivatives, differentiation was the process of taking a derivative. So we now have an anti-differentiation. Okay, which just is the opposite of differentiation. Anti-differentiation is the process of finding an antiderivative. Now, anti-differentiation is also sometimes referred to as indefinite integration. So now what we're starting with in Chapter 4 is working with integration or integral calculus. Calculus, at least the part of calculus that we study in Calc 1, is pretty much made up of two main topics: differentiation, taking derivatives and all the stuff that you can do with derivatives, and integration, which is the same thing as anti-differentiation. And then, so we're going to be talking about integrals. And we will eventually be looking at many of the different things, applications of integrals or antiderivatives. All right. What I'd like for you to do next is take a look. I'm going to give you some examples to work. And I want you to find antiderivative, find an antiderivative for each of these functions. F of x equals 2x. F of x equals x. F of x equals x squared. F of x equals 1 over x squared. F of x equals 1 over x cubed. And f of x equals cosine x. Pause the tape. And think about, what function can I take a derivative of and have the derivative be 2x? What function can I take a derivative of and have the derivative be x? And so on. So pause the tape now, do some work, and then when you've gotten each of these 6 antiderivatives, start the tape again and check your answers. All right, answers for each of these. The antiderivative for 2x is going to be x squared. Remember to put the plus c. So that's going to take care of all the possible antiderivatives, all the possible functions that you could take a derivative of and have the answer be 2x. So that's the answer for number 1. Number 2, antiderivative of x. Okay, think about it. I've got a power of 1, so what power I'd have to take a derivative of to make the power be 1 would have to be x squared. And then I've got to have a constant in front there so that when I multiply 2 by that constant, the coefficient becomes a 1. So that is 1/2. For number 3, the antiderivative, and I'm kind of talking you through my thought process. The power on the antiderivative needs to be a 3. So I'm going to have a 1/3 coefficient in front of the x cubed, so that when I take the derivative, 1/3 times 3 becomes 1. Number 4, you might want to think about that as x to the minus 2 power. I think it makes finding the antiderivative a little bit easier if you think about it that way. So the power on the antiderivative function has to be -1. So I'm going to have -1 as the coefficient. Okay, and remember, think about how you can check each of these answers. If I want to check to make sure that this function, capital F of x, that I've written is actually the antiderivative for the function x to the minus 2 power, I can just take a derivative of this. Okay, and I'll go back and erase this in a second. But think about it. Power rule, -1 times -1 is +1 times x. Subtract 1 from the power. Derivative of a constant is 0. So there's the derivative function, which matches exactly the function I had to start with. So I know my antiderivative is correct. So number 5, I'm going to think about that function as x to the minus 3rd power. So the antiderivative, power on x has to be a -2. My coefficient in my derivative function is +1, so I need a coefficient in my antiderivative to be -1/2, because -2 times -1/2 is +1. And I remember to put the plus c on the end. For number 6, what function has a derivative that is equal to cosine x? Okay, it's obviously going to be one of our trig functions, sine or cosine, tangent, something like that. So I stop and I think about my derivative rules. Derivative of sine is cosine. So that means the antiderivative of cosine has to be sine of x. All right. Now, each of these plus c's that we put in our antiderivatives, the plus c that's on each one of those is called the constant of integration. And that constant of integration is very important. It needs to be there in your function, or else you have not taken into account all the possibilities for the antiderivative. Now, the function that we're getting, capital F of x, for each of these problems, is what we refer to, or at least the function in the form that we've got with the plus c on it, is called the general antiderivative. So a general antiderivative will always have plus c, the constant of integration, included in it. Okay, that general antiderivative is also sometimes referred to as the general solution to the differential equation. So, general solution to the differential equation. Basically, a differential equation is an equation that involves a derivative. Okay, so if you're talking about functions in x and y, a differential equation is an equation that has x, it has y, and it has the derivative of y with respect to x, dy over dx or y prime. So kind of maybe an oversimplified way to define a differential equation is you can think of it as an equation involving a derivative. So in that sense, each of the derivative functions, each of the lowercase f of x functions we had in the previous example was a differential equation. The solution to a differential equation is another equation. It is the equation that you could differentiate to get what you started with. So if you've got a problem like this, we want to find the general solution to the differential equation. I should put the word 2 in there. To y prime is equal to 5. So what you're being asked to do is, okay, we have the derivative function. We know what y prime is. Find an equation for y. So anti-differentiate the constant 5. Think about what would I take a derivative of and have the derivative be equal to 5? Well, that's going to be 5x. Remember the plus c. So the equation y equal 5x plus c is the solution to your differential equation. Now, differential equation notation you're going to see, you may see something like this. dy over dx is equal to some function of x, okay, which is really what we had in the previous example. dy over dx is the same thing as y prime. 5 is some function of x. So we've got dy over dx equal a function of x there. Now, if you have that, then it's also accurate to say that dy is equal to the function f of x times dx. So what we kind of have there is we start with derivative notation, dy over dx, and we end up with differential notation. dy is the differential y, dx is the differential x. Extend this page just a little bit further, and that's going to be the end of my page. Now, the symbol that we use to indicate that we want to take an antiderivative or to find an indefinite integral looks like this, kind of a stretched out S. That's called an integral sign. So if we have the antiderivative or integral of f of x dx, that means the antiderivative of f with respect to x. Antiderivative of function f with respect to variable x. Oops, with respect to, it's two different words. Respect to x. Okay, that is also called the indefinite integral of f with respect to x. Page. So the stretched out s, I mentioned before, that's called the integral sign. So I will refer to that as the integral sign. I'm not going to call it a stretched out s. The function that we have with the integral sign, the f of x, is called the integrand. So the integrand is the function we are anti-differentiating. And then the dx that's stuck on the end. And you're going to have dx, or if your variable in your function is y, you'd have dy stuck on the end. Or if the variable in your function was t, you'd have dt stuck on the end. Anytime you have an integral sign, that integral is going to end with either dx or dt or dy or d something, d variable. And that notation tells us what variable the function is in. Okay? So the dx, when we had the integral of f of x dx, when we had that notation, that indicates that we're going to take an antiderivative, and the variable in our antiderivative, the variable in the function we get, should be x. So the dx indicates the variable of integration. So integration, where you're taking an antiderivative, and differentiation, where you're taking a derivative, those are inverse functions, probably not the right word. Those are inverses. Finding a derivative and finding an antiderivative are opposites. So integration, since integration and differentiation are inverses, if we need to take the integral of a derivative, well, that's going to take us right back to the original function, plus c. So the antiderivative, and this is probably worth writing down so you'll have it to look at, the antiderivative of a derivative. Wow. Handwriting struggling. Oops, sorry, guys, starting over. The antiderivative of a derivative is the original function. With the possible exception, they may possibly, the original function and your new function you got after you've taken an antiderivative of a derivative, they might differ by a constant. So they possibly differ by a constant. All right, so if we differentiate, okay, remember that notation means we're going to take the derivative with respect to x. If we differentiate an antiderivative, we will get the integrand. So if you've taken a derivative first, and then you anti-differentiate, you're going to get the original function, and we might possibly, you're going to get, you've basically kind of worked yourself around in a circle. The only possible difference is a constant. If you do those operations in the other order, which is what I have written here, if you anti-differentiate or integrate first, and then you take the derivative of your integral, you're going to get exactly what you started with. So anti-differentiation or integration is the opposite of finding derivatives. So all of the derivative rules and all of the derivative formulas you have learned, you just do those in reverse. You do the opposite, and that's your integral formula. There are some integral formulas, actually a very nice list. Look at page 250 in your textbook. I'm not going to write all those down because they're in your book for you. I expect you to know those well enough to be able to use them. And to be quite honest, if you've done your work to learn your derivative rules, then being able to think about those derivative rules in reverse is not going to be that big a deal. So if I were you, I would actually take the time. You can do it right now. You can stop this recording if you want to and actually write these rules in your notes right now, or you can wait and do it at the end of class, okay, after you watch the whole video. It doesn't matter, but I think it's worth getting those right, taking the time to write down the derivative rule and the integral rule, integration rule that goes with it. So you're thinking, I know how to take the derivative, I just do it backwards to take the antiderivative. All right, let's check. Okay, integrate 5x dx. Now, if we're going to do that, if we're using our integration rules, okay, so if you have your book open, glance at those. The second rule down the page, no, excuse me, I take that back. It's the third line down the page. We've learned that if we're going to differentiate a constant times a function, we can just differentiate the function, differentiate the x part, and leave the constant out in front. We have a very similar rule for working with antiderivatives. This integral can be rewritten as 5 times the integral of x. And then it's just a matter of working with the power rule. The antiderivative of x is 1/2 x squared. Don't forget your plus c. So our antiderivative is 5/2 x squared plus c. Or the value of the integral of the function 5x dx is 5x squared, 5/2 x squared plus c. Another example, integral of 1 over x to the 4th dx. We want to rewrite that as x to the -4th power dx. And the power rule for working with antiderivatives, instead of subtracting 1 from the power, we're going to add 1. And when you've got negative powers, be careful. You are adding 1 to -4. It's going to take you to -3. And then you divide by that new power. So if we wanted to clean that up, we could write that as the opposite of 1 over 3x cubed plus c, and that looks a little bit nicer. Integral of square root of x dx. Think of the square root as a 1/2 power. Then apply the power rule. So if we add 1 to 1/2, we get 3/2. And then we're going to divide by 3/2. Now, a nicer way of writing that is 2/3 times x to the 3/2 power. integral of 3 times cosine x dx. You can pull the 3 out front and then just have to think about integrating cosine of x. Oops. Antiderivative of cosine is sine of x. So our integral is 3 sine x plus c. Now, it is worth actually writing down, so bear with me while I get ready to do that. You can always check your antiderivatives. Differentiate your answer. So check antiderivatives by taking the derivative. We didn't necessarily have a way to check our derivatives, but since we do know the derivative rules and we know them well, we can check our antiderivatives by differentiation. All right, some more examples of working with derivatives. Let me get a new sheet of paper and change my pen back. What if you see integral of dx? Okay, it doesn't look like there's a function in there. Remember that there would be an understood 1. We don't always have to write the coefficient 1. So this is the same thing as saying the integral of 1 times dx. And so your thought process is, what can I take a derivative? What function has a derivative equal to 1? And that's x plus c. If you have an antiderivative of a function that has more than one term, you can break that down into smaller pieces. So I can rewrite this as the antiderivative of x dx plus the antiderivative of 4 dx. Now notice that a dx gets stuck on both integrals. Every time you write the integral sign, you've got to have the dx on the end of it. So integrating then, we get 1/2 x squared for the first part plus 4x for the second part, remembering plus c on the end. Now you know, with enough practice, you're going to be able to skip that second step. You can go straight from the integral of x plus 4 to 1/2 x squared plus 4x plus c. But you're not ever going to be penalized for writing down more steps than you need to. So if you're not sure, break it down. Integral of, we have a nice polynomial function this time, 3x to the 4th power minus 5x squared plus x dx. Now, do please notice that when you are anti-differentiating a function that has more than one term, the integrand in that equation at the top, the integrand x plus 4 is in parentheses. You've got to be very clear that it is the entire expression x plus 4 that you're anti-differentiating. Same thing with the next problem that I have written down. 3x to the 4th minus 5x squared plus x is the integrand. So I need to make it clear that I am anti-differentiating all of that, put it in parentheses. Then you can break it down further, and I can rewrite this as 3 times the integral of x to the 4th power dx minus 5 times the integral of x squared dx plus the integral of x dx. So 3 times 1/5 x to the 5th power minus 5 times 1/3 x cubed plus 1/2 x squared. Now, technically, each of those individual integrals should have a plus c. You don't have to do that. If you add up all your constants, you're going to get another constant, so it's absolutely okay with me if you just write plus c at the end. So our final antiderivative is 3/5 x to the 5th power minus 5/3 x cubed plus 1/2 x squared plus c. All right, we need to integrate x plus 1 divided by square root of x. We're going to have to do a little bit of work to this before we can get it in a form where we know what to do with the antiderivative. So think about this. I can put that, I can kind of separate that as x over square root of x plus 1 over square root of x. If you think about adding those two fractions together, you would end up with x plus 1 all over the same denominator, square root of x. And then you can simplify each individual term. So this would end up being 1 over square root of x in the first term. No, sorry, that's not right. That would be, that's going to simplify to square root of x plus 1 over square root of x. Can't really simplify that term at all. Rewrite those with exponents instead of square roots. And then apply the power rule. 2/3 x to the 3/2 plus. Now think about adding 1 to negative 1/2. You're going to get positive 1/2. Divide by 1/2 is the same thing as multiplying by 2, so that's the same thing as 2 times x to the positive 1/2 power plus c. So what I'm thinking is negative 1/2 plus 1 is positive 1/2. So that's the new power, and that's what I have to divide by. All right, one more. We need to integrate cosine x over sine squared x dx. You need to be a little creative there. Look back at your integration formulas. You know, if we had the integral of just cosecant squared, 1 over sine is cosecant, we know how to antidifferentiate that, okay, if we know the formula. Well, we don't have just 1 over sine squared. If we had, you know, just cosine, we could antidifferentiate that. That doesn't really fit what we've got. So think about this. I can rewrite that fraction as a product of the fraction 1 over sine x times cosine over sine x. Or cosecant x times cotangent x. So what you want to do is try to rewrite your integrand so that it is in a form so it looks like one of the formulas that we know. And looking at the list, the very last integral at the bottom is the antiderivative of cosecant x times cotangent x. And that is going to be negative, nope, not cotangent, negative cosecant x plus c. Think about it. The derivative of cosecant is negative cosecant cotangent. So the derivative of cosecant, the antiderivative of cosecant cotangent is going to be negative cosecant. That's a little bit harder than maybe some of the others. All right, new page. So each of these problems that we've done, each of those antiderivatives we just found, gave us general solutions. Okay, they were the general antiderivatives. If we're going to be able to find a specific or a particular solution, we're going to have to know a little more information. So to find the particular solution, to an antiderivative, you need more info. So think about this. Integrate the function 3x squared minus 1 dx. Okay, so x cubed minus x plus c. We've talked about the fact that that constant c can be any number. So grab your calculator. Okay, and I'm going to grab my